NDCG can improve while one group disappears below the fold. Position discounted exposure shows who the ranker makes visible and what a fairer order costs in relevance. You'll learn the shape of a workflow that audits ranked results for group visibility gaps and relevance preservation. I'm Professor Pi, teaching search and IR with simple Python. Lots of teams tune for relevance and then assume the top results are seen. But equal total relevance can still hide a whole group below the fold. For a product team, that might mean one seller or one author never gets clicks, even though their relevance is on par. The mental model is straightforward. Convert ranked positions into numbers that estimate attention per group. Then ask whether changing the order to boost visibility would cost relevance as measured by NDCG. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. We'll build a tiny toy ranking where the visibility gap is obvious. Then measure exposure, compute NDCG, try a fairer order, and pick a candidate that balances both. This snippet builds the smallest ranking where exposure bias becomes visible. The list keeps each document ID, group label, and graded relevance together, so the order is obvious on screen. The key setup is that rel shows both groups sum to the same total relevance, while every A item is listed before every B item. That separates relevance parity from visibility, which is exactly where ranking fairness questions become interesting. The printed output confirms the size and the equal group relevance, giving us a clean baseline before we turn positions into attention numbers. Seeing the raw list helps, but we still need a principled way to turn positions into visibility. Next, we add a discount that models how users scan results. This code turns rank positions into visibility weights using log discounts. A document near the top contributes more exposure than the same document lower down, mirroring the simple inspection model behind many IR metrics. The exposure dictionary then sums those discounted weights by group using the current ranking order, not relevance. Because rel tied the groups on total relevance, any difference here is driven by placement. The printed values make it clear. Group A gets much more discounted visibility than Group B, which is the exposure gap we want to track. Exposure is necessary, but product decisions care about relevance too. So we compute utility from the graded labels and compare to the relevance optimal ordering. This example adds the relevance side of the evaluation and gives us an NDCG baseline. The gain function maps graded relevance into the usual exponential utility scale, and DCG applies the same position discounts we used for exposure. Ideal is the relevance sorted ordering, so NDCG compares the observed ranking to the best relevance-only ordering for this query. The important takeaway is that utility can look strong while visibility stays uneven. The output shows a high NDCG, which is exactly why exposure measurements are needed. With both exposure and relevance measured, we can try a counterfactual ordering and see how the exposure gap responds. This snippet tests a concrete ranking change rather than just diagnosing the original order. Re-ranked interleaves equally relevant A and B items, so high visibility slots are shared more evenly. Fair X recomputes exposure on that alternative, while old gap and new gap convert the group totals into a single disparity number. This is a counterfactual test. Same documents, same relevance labels, different ordering. The output reports how much the exposure gap drops, making the visibility gain from the re-rank easy to compare. One re-rank is good for intuition, but a product decision needs a selector. Keep relevance above a floor while minimizing disparity. The final snippet demonstrates that choice. This code turns the metrics into a tiny selection baseline. Cans holds 3 plausible orderings. Scores stores each candidate's NDCG and exposure gap. And eligible filters out any ranking that falls below the relevance floor. The final min call picks the remaining ranking with the smallest exposure disparity. Raising the NDCG threshold makes the selection more conservative about relevance loss. Lowering it gives fairness-oriented re-rankers more room to move documents. The output names the selected candidate and its disparity, closing the loop between visibility and relevance preservation. To map this toy flow to a real system, run the same steps per query across a held-out log. Aggregate per query exposure gaps to find persistent patterns, and report both average NDCG and average exposure gap so stakeholders can weigh the trade-offs. 3 quick takeaways. Measure exposure bias when groups have comparable relevance but different placement. Use a position-discounted exposure to mirror user attention and compare it to NDCG to protect relevance. And remember, high NDCG does not guarantee equal visibility. A sensible next step is to tune the NDCG threshold used to filter eligible candidates on a real query log or evaluation set. Increasing the threshold tightens relevance preservation. Decreasing it gives the re-ranker more room to equalize exposure. If short, practical IR helps, subscribe and watch the IR videos.